It appears there was an error in a previous National Electrical Code (NEC). Specifically, the issue concerns neutral conductor sizing within a three-phase, four-wire, wye-connected system. According to the last sentence of section 220.22 DON, the neutral conductor should not be required to be larger than the phase conductors when services are supplied from such a system. However, there was an inconsistency in an earlier example within the NEC. This inconsistency has since been addressed and corrected in the 2020 NEC. The revised wording in the 2020 edition clarifies this point. The updated sentence in 220.22 DON now states that the neutral conductor shall not be required to be larger than the phase conductors for services supplied from a three-phase, four-wire, wye-connected system except as otherwise provided in this section. The exception refers to section 220.22 D3. This exception outlines specific instances where the neutral conductor is, in fact, required to be larger than the phase conductors. These situations generally involve services supplied from a transformer bank or a generator that is not connected in a wire configuration. To reiterate, in most standard three-phase, four-wire, wye-connected services, the neutral conductor's size is typically not required to exceed that of the phase conductors. However, it's crucial to consider the exception described in 220.22 D3. This section mandates a larger neutral conductor in scenarios where the power source, either a transformer bank or a generator, lacks a wye configuration. In such cases, the neutral conductor must be sized appropriately to handle the potential unbalanced load. The correction in the 2020 NEC aims to provide clarity and consistency in the application of neutral conductor sizing rules. Always refer to the most current edition of the NEC and consult with a qualified electrical professional for specific applications. It is important to understand the requirements outlined in section 220.22 D3, which dictates the need for a larger neutral conductor in certain scenarios. This typically arises when dealing with power sources like transformer banks or generators that deviate from the standard wye configuration. The absence of a wye connection can lead to significant neutral current, necessitating a larger conductor to safely handle the increased load. Ensuring correct neutral conductor sizing is critical for the safe and efficient operation of electrical systems. Undersized neutral conductors can overheat, leading to insulation damage, fire hazards, and system malfunction. Therefore, adherence to the NEC guidelines and proper engineering practices are essential. Now let's delve a little deeper into the technical aspects of neutral conductor sizing and the reasons behind these code requirements. In a balanced three-phase, four-wire, wye-connected system, the neutral conductor ideally carries minimal current. This is because the currents in the three-phase conductors are 120 degrees apart, and their vector sum theoretically equals 0 at the neutral point. However, in reality, electrical loads are rarely perfectly balanced. Imbalances can arise due to a variety of factors, such as unequal distribution of single-phase loads across the three phases, nonlinear loads that generate harmonic currents, and variations in equipment operating characteristics. These imbalances cause current to flow in the neutral conductor. The magnitude of this neutral current depends on the degree of imbalance in the system. In situations where the imbalance is significant, the neutral current can be substantial, potentially exceeding the current in any one of the phase conductors. This is why the NEC mandates specific rules for neutral conductor sizing, ensuring that it can safely carry the anticipated neutral current. The NEC provides guidelines for calculating the neutral load based on the types of loads connected to the system. For example, for household electric ranges and dryers, a demand factor of 70% is often applied to the neutral load calculation, recognizing that these appliances do not typically operate at their full rated capacity continuously. However, for nonlinear loads, such as those found in electronic equipment, the neutral current can be significantly higher than the phase current due to the presence of harmonic currents. Harmonic currents are multiples of the fundamental frequency, typically 60 Hz in the United States. Odd-order harmonics, such as the third, fifth, and seventh, are particularly problematic because they do not cancel out in the neutral conductor. Instead, they add arithmetically, resulting in a potentially large neutral current. To mitigate the risks associated with harmonic currents, the NEC requires that the neutral conductor be sized to carry the maximum unbalanced load, including the harmonic currents. This often necessitates the use of an oversized neutral conductor, especially in buildings with a high concentration of electronic equipment such as office buildings, data centers, and hospitals. Furthermore, the NEC also addresses the issue of voltage drop in neutral conductors. Excessive voltage drop can negatively impact the performance of sensitive electronic equipment and can even lead to equipment malfunction. To minimize voltage drop, the NEC specifies minimum conductor sizes based on the length of the circuit and the amount of current it carries. In addition to the NEC requirements, it is also important to consider the recommendations of equipment manufacturers and industry standards when sizing neutral conductors. Some manufacturers may specify larger conductor sizes than those required by the NEC to ensure optimal performance and reliability of their equipment. The use of oversized neutral conductors can also provide additional benefits, such as reduced impedance and improved system efficiency. Lower impedance can help to reduce voltage distortion and improve power quality, while improved efficiency can lead to lower energy consumption and reduced operating costs. In summary, the proper sizing of neutral conductors is a critical aspect of electrical system design and installation. Adherence to the NEC guidelines, consideration of load characteristics, and attention to voltage drop are essential for ensuring the safe, reliable, and efficient operation of electrical systems. It is always advisable to consult with a qualified electrical professional to determine the appropriate neutral conductor size for specific applications. Now let's discuss how to calculate the neutral conductor size in a three-phase, four-wire, wye-connected system, considering both balanced and unbalanced loads, as well as harmonic currents. Firstly, determine the total connected load on each phase. This involves summing the volt-ampere for ratings of all the loads connected to each phase. Secondly, apply any applicable demand factors. The NEC allows for the application of demand factors to reduce the calculated load based on the assumption that not all loads will operate simultaneously at their full rated capacity. Demand factors vary depending on the type of load and the occupancy. Consult the NEC for the appropriate demand factors for specific applications. Thirdly, calculate the maximum unbalanced load. The maximum unbalanced load is the difference between the largest phase load and the smallest phase load. This represents the amount of current that will flow in the neutral conductor due to the imbalance in the system. Fourthly, determine the harmonic content of the loads. If the system includes nonlinear loads that generate harmonic currents, it is necessary to estimate the magnitude of these harmonic currents. This can be done by consulting with equipment manufacturers or by using harmonic analysis software. Fifthly, calculate the neutral current due to harmonic currents. The harmonic currents in the neutral conductor are typically the odd-order harmonics, such as the third, fifth, and seventh. These harmonics add arithmetically in the neutral conductor, so the total neutral current due to harmonics is the sum of the individual harmonic currents. Sixthly, calculate the total neutral current. The total neutral current is the vector sum of the unbalanced load current and the harmonic current. In most cases, the unbalanced load current and the harmonic current are assumed to be in phase, so the total neutral current is simply the arithmetic sum of the two currents. Seventhly, select the appropriate conductor size. Once the total neutral current has been calculated, the appropriate conductor size can be selected based on the ampacity of the conductor. The ampacity is the maximum amount of current that a conductor can carry safely without exceeding its temperature rating. The NEC provides tables of ampacities for various conductor types and sizes. Eighthly, consider voltage drop. In addition to ampacity, voltage drop must also be considered when selecting the conductor size. The NEC recommends that the voltage drop in the neutral conductor should not exceed 3% of the supply voltage. If the calculated voltage drop exceeds this limit, a larger conductor size must be selected. Ninthly, apply any applicable correction factors. The ampacity of a conductor may need to be derated if it is installed in certain conditions, such as in a hot environment or in a conduit with other current-carrying conductors. The NEC provides correction factors for various installation conditions. Tenthly, verify the conductor size. After selecting the conductor size, it is important to verify that it is adequate for the intended application. This can be done by performing a load flow study or by consulting with a qualified electrical professional. By following these steps, the neutral conductor can be sized appropriately to ensure the safe, reliable, and efficient operation of the electrical system. Now, let's consider a practical example to illustrate the process of neutral conductor sizing. Suppose we have a 3-phase, 4-wire, wye-connected system supplying a small office building. The building has the following loads: phase A 20 amps of lighting, 15 amps of receptacles, and 10 amps of HVAC. Phase B 25 amps of lighting, 20 amps of receptacles, and 12 amps of HVAC. Phase C 18 amps of lighting, 12 amps of receptacles, and 8 amps of HVAC. Assume that the system also includes nonlinear loads that generate the third harmonic current of 5 amps in the neutral conductor. Firstly, calculate the total connected load on each phase. Phase A 20 amps plus 15 amps plus 10 amps equals 45 amps. Phase B 25 amps plus 20 amps plus 12 amps equals 57 amps. Phase C 18 amps plus 12 amps plus 8 amps equals 38 amps. Secondly, apply any applicable demand factors. For lighting and receptacles, a demand factor of 100% is typically used. For HVAC, a demand factor of 75% may be applied. Phase A 45 amps x1 equals 45 amps. Phase B 57 amps x1 equals 57 amps. Phase C 38 amps x1 equals 38 amps. Thirdly, calculate the maximum unbalanced load. The largest phase load is 57 amps, and the smallest phase load is 38 amps. The maximum unbalanced load is 57 amps minus 38 amps equals 19 amps. Fourthly, determine the harmonic content of the loads. The third harmonic current is given as 5 amps. Fifthly, calculate the neutral current due to harmonic currents. The neutral current due to harmonics is 5 amps. Sixthly, calculate the total neutral current. The total neutral current is the sum of the unbalanced load current and the harmonic current. Total neutral current is 19 amps plus 5 amps equals 24 amps. Seventhly, select the appropriate conductor size. Based on the NEC tables, a number 12 AWG copper conductor has an ampacity of 25 amps. This is sufficient to carry the total neutral current of 24 amps. Eighthly, consider voltage drop. Assuming a circuit length of 100 feet, the voltage drop in a number 12 AWG copper conductor carrying 24 amps is approximately 2.4 volts. This is less than the recommended limit of 3% of the supply voltage. Ninthly, apply any applicable correction factors. If the conductor is installed in a hot environment or in a conduit with other current-carrying conductors, the ampacity may need to be derated. Tenthly, verify the conductor size. The selected conductor size of number 12 AWG copper is adequate for the intended application. However, it is always advisable to consult with a qualified electrical professional to verify the conductor size and to ensure that all applicable codes and standards are met. This example illustrates the basic steps involved in neutral conductor sizing. However, the actual calculations can be more complex, depending on the specific characteristics of the electrical system. It is important to carefully consider all of the relevant factors and to consult with a qualified electrical professional to ensure that the neutral conductor is sized appropriately. Finally, let's address some common misconceptions regarding neutral conductor sizing. One common misconception is that the neutral conductor is always smaller than the phase conductors. While this is often the case in balanced three-phase systems, it is not always true. As we have discussed, in systems with significant imbalanced loads or harmonic currents, the neutral conductor may need to be larger than the phase conductors. Another misconception is that the neutral conductor only carries current when there is an imbalance in the system. While it is true that the neutral conductor carries current due to imbalanced loads, it can also carry current due to harmonic currents, even in a perfectly balanced system. A third misconception is that voltage drop in the neutral conductor is not important. Voltage drop in the neutral conductor can have a significant impact on the performance of sensitive electronic equipment and can even lead to equipment malfunction. Therefore, it is important to consider voltage drop when sizing the neutral conductor. By understanding these common misconceptions and by following the guidelines outlined in the NEC, electrical professionals can ensure that neutral conductors are sized appropriately to provide safe, reliable, and efficient electrical systems. The NEC serves as a comprehensive guide, but practical application requires a thorough understanding of electrical principles and load characteristics. Consulting with experienced engineers and utilizing specialized software tools can further enhance the accuracy and effectiveness of neutral conductor sizing calculations. Remember that safety is paramount, and any uncertainty should be addressed with a qualified professional.